Large Telescope, VLT, in Chile, have been instrumental in identifying these compounds. The presence of methane ice, in particular, draws parallels with both Pluto and Neptune's moon Triton, suggesting commonalities in the processes that shape these distant objects. The surface of this distant world is believed to be extremely cold, with temperatures averaging around -243 degrees Celsius. At such frigid temperatures, volatiles like nitrogen and methane freeze solid, forming an icy crust that reflects sunlight with a moderate degree of brightness. Makemake's albedo, or reflectivity, is higher than that of most other Kuiper belt objects, KBOs, which has aided in its detection and characterization. Makemake orbits the Sun at an average distance of about 45.7 astronomical units, AU, equivalent to roughly 6.8 billion kilometers. Its elliptical orbit takes it around the Sun once every 305 Earth years, with a slight inclination of 29 degrees relative to the plane of the Solar System. This inclined trajectory places Makemake among the dynamically hot KBOs, which have orbits more tilted and eccentric than the cold classical KBOs like Quasar. One of the most intriguing aspects of this Kuiper belt object is its lack of a significant atmosphere. Unlike Pluto, which experiences seasonal atmospheric changes due to the sublimation of nitrogen and methane ices, Makemake's tenuous atmosphere, if present at all, is likely composed of trace amounts of methane and nitrogen. Observations during stellar occultations, when the dwarf planet passes in front of a distant star, have provided valuable constraints on its atmospheric properties. These events reveal a sharp drop in brightness, indicative of a lack of a substantial gaseous envelope. In 2016, the Hubble Space Telescope made a groundbreaking discovery by identifying a small moon orbiting Makemake. This satellite, unofficially nicknamed 2 Malawian Kwachas, is estimated to have a diameter of about 175 kilometers. It's the trans-Neptunian body, known as Makemake, stands as a remarkable example of the icy worlds populating the outer reaches of our solar system. This celestial object, part of the Kuiper belt, occupies a region teeming with primordial remnants from the early formation of the Sun and its planetary system. Since its discovery in 2005 by a team of astronomers led by Michael E. Brown, the frozen sphere has captivated scientists eager to unravel the mysteries of these distant and enigmatic objects. This dwarf planet, the third largest among its peers, boasts a diameter of approximately 1,430 kilometers, situating it in the same category as Pluto and Eris. Unlike the inner rocky planets or the gas giants, the icy surface of this world is composed primarily of frozen methane, ethane, and other hydrocarbons, which give it a reddish hue. Spectroscopic analyses, carried out with advanced telescopes like the Very Large Telescope, VLT, in Chile, have been pivotal in uncovering the chemical composition of the Kuiper belt object. Orbiting at an average distance of 45.7 astronomical units, AU, from the Sun, this remote sphere takes approximately 305 Earth years to complete a single orbit. Its elliptical path, inclined by 29 degrees relative to the ecliptic plane, distinguishes it from many other solar system objects. These orbital characteristics classify the icy body as part of the dynamically hot population of the Kuiper belt, where orbits tend to be more eccentric and inclined than the cold population. Interestingly, this far-off world exhibits a surface that is highly reflective, with an albedo higher than that of most other trans-Neptunian objects. This bright reflectivity, coupled with its size, made it a relatively easier target for telescopes to detect compared to smaller, darker Kuiper belt objects. Its icy crust, composed of solidified methane and nitrogen, reflects sunlight with a unique reddish tint, linking this distant body to other notable objects like Pluto and Triton, Neptune's large moon. Unlike Pluto, however, this celestial body lacks a significant atmosphere. Stellar occultations, events where the icy sphere passes in front of a background star, have revealed that it does not possess the thick layers of nitrogen and methane gas seen on its sibling dwarf planet. At its average surface temperature of -243 degrees Celsius, any gases would freeze rapidly, leaving only a tenuous, almost imperceptible envelope of methane molecules. Adding to the intrigue, in 2016, astronomers using the Hubble Space Telescope uncovered a faint satellite orbiting this frozen world. The Moon, provisionally labeled 2 Malawian Kwacha's, is estimated to be about 175 kilometers in diameter. The discovery of this satellite has opened new doors for research, allowing scientists to measure the mass and density of the dwarf planet with greater precision. By observing the orbital dynamics of 2 Malawian Kwacha's, researchers aim to gain deeper insights into the internal structure of this trans-Neptunian object and its formation history. The discovery of this moon also hints at the possibility that this distant body underwent a significant collision event in the past, similar to the impacts theorized for other dwarf planets and their moons. Such events are thought to have played a critical role in shaping the Kuiper belt as we observe it today, providing clues to the early chaotic phase of the solar system's evolution. This icy world's methane-rich surface composition links it chemically to Pluto and Triton, suggesting a shared evolutionary pathway for these distant objects. Methane, one of the simplest hydrocarbons, plays a vital role in determining the color and reflectivity of this frigid world. The reddish hue observed on its surface is likely the result of complex organic molecules, known as tholins, formed through the interaction of methane with ultraviolet radiation from the Sun. These tholins are common on outer solar system bodies and are responsible for the strikingly varied colors of trans-Neptunian objects. Scientists hypothesized that the distant sphere's lack of significant nitrogen ice might be due to its smaller size and weaker gravity, which would make it more difficult for the object to retain lighter gases over billions of years. This hypothesis contrasts sharply with Pluto, which has managed to sustain a thin but dynamic nitrogen-rich atmosphere. The comparative study of these worlds offers a glimpse into the diversity of conditions and evolutionary pathways among objects in the outer solar system. Further investigations into this Kuiper belt member have been bolstered by advanced telescopic technologies and computational modeling. Observations using infrared spectroscopy have provided evidence for seasonal changes on the surface of this frozen sphere. These changes, though far less dynamic than those on Earth or Mars, hint at subtle shifts in the distribution of ices as the dwarf planet travels through its elongated orbit around the Sun. The exploration of this enigmatic object has also fueled discussions about potential spacecraft missions to the Kuiper belt. While current missions, such as NASA's New Horizons probe, have provided invaluable data on similar bodies, a dedicated mission to this dwarf planet and its moon could revolutionize our understanding of the outer solar system. By studying this world up close, scientists could analyze its geology, surface chemistry, and potential subsurface layers, answering long-standing questions about the building blocks of planets and the processes that govern their evolution. This frozen world, residing in the cold and distant reaches of the solar system, represents a time capsule of early solar system materials. Its study not only sheds light on the dynamics of the Kuiper belt but also provides broader insights into the mechanisms that drive planetary formation and migration. Through ongoing research and future exploration, the mysteries of this icy body continue to inspire curiosity and expand the boundaries of human knowledge. The frozen orb stands as a crucial key to understanding the broader landscape of the Kuiper Belt, a region that serves as a repository for ancient materials from the dawn of the solar system. Unlike the rocky planets of the inner solar system or the gas giants further out, this remote celestial body represents a category of icy worlds that formed in the outermost reaches, where the sun's warmth is but a faint glow. Its composition, structure, and orbit together create a unique portrait of conditions far removed from those familiar to earthbound observers. One of the remarkable features of this Kuiper Belt resident is its stability over time. Despite its vast distance from the Sun and its relatively small size, the dwarf planet has maintained a consistent orbital path for billions of years. This stability has allowed astronomers to study the interactions between it and other trans-Neptunian objects, offering critical insights into the gravitational dynamics of the outer solar system. The inclined orbit of this icy body, with its significant tilt compared to the plane of the solar system, suggests a turbulent past. It is likely that gravitational interactions with Neptune, or perhaps with other large Kuiper Belt objects, played a role in shaping its current trajectory. The absence of significant atmospherics on this distant sphere has not deterred scientists from probing its surface for clues about its evolutionary history. High-resolution imaging and spectroscopy have revealed a patchwork of icy materials, including solid methane and ethane, alongside traces of more complex organic molecules. These compounds, while frozen solid under the extreme cold, bear evidence of photochemical reactions driven by the faint sunlight and cosmic rays that permeate the outer solar system. The reddish tint that characterizes its surface is a hallmark of such processes, with tholins, organic residues formed from methane, providing the distinctive coloration. Further exploration of this icy sphere's surface has revealed intriguing hints about its geological processes. While its small size and low gravity likely prevent tectonic activity or large-scale volcanism, there is evidence to suggest that sublimation and deposition cycles may occur on a seasonal basis. As the frozen world moves closer to the Sun in its elliptical orbit, some of its methane and nitrogen ices could transition directly from solid to gas, creating transient atmospheric effects or causing slight changes in the surface texture. These processes, though subtle, are of immense interest to planetary scientists, as they mirror phenomena observed on other Kuiper Belt objects like Pluto. The discovery of a small satellite orbiting this celestial object has added a new layer of complexity to its study. 2 Malawian Quachas, as the Moon is informally known, is much darker than its parent body, reflecting only a fraction of the sunlight. This stark contrast in albedo suggests that the Moon and its host may have originated under different circumstances. One prevailing theory is that the satellite was formed as a result of a massive collision, similar to the events that are thought to have created Pluto's moon system. Such a collision would have ejected material from the surface of the icy world, which later coalesced to form the smaller companion. The existence of 2 Malawian Quachas also provides astronomers with a unique tool for studying the mass and density of the frozen orb. By carefully tracking the motion of the Moon around its primary, scientists can calculate the mass of the entire system, shedding light on its internal composition. Early estimates suggest that the density of this Kuiper Belt resident is lower than that of Pluto but higher than some smaller trans-Neptunian objects, implying a mixture of rock and ice in its interior. These findings hint at a layered structure, with denser materials concentrated in the core and lighter ices forming the outer shell. In addition to its intrinsic scientific value, the study of this remote celestial body holds broader implications for understanding the history of our solar system. The Kuiper belt, of which this dwarf planet is a part, is believed to be a remnant of the primordial disk of gas and dust that gave rise to the Sun and its planets. By analyzing the composition and distribution of these icy objects, researchers can reconstruct the conditions that prevailed during the early stages of planetary formation. This frozen sphere, with its pristine ices and unaltered surface features, serves as a time capsule preserving the chemical and physical processes that shaped the solar system's infancy. The implications of studying this distant world extend beyond the confines of our solar system. Similar icy bodies are thought to populate the outer regions of other planetary systems, where they may serve as building blocks for planets or as reservoirs of water and organic materials. Understanding the processes that govern the evolution of this frozen orb can therefore provide valuable insights into the potential surface and surroundings. These instruments have opened new windows into the chemistry and physics of the frozen world, revealing intricate details that were once beyond the reach of human knowledge. Future missions to this icy sphere, though technically challenging, are already being considered. A spacecraft equipped with advanced imaging systems and spectrometers could map its surface in unprecedented detail, revealing the distribution of ices, organics, and other materials. Such a mission could also investigate the properties of two Malawian quachas, providing a more complete picture of the system as a whole. By venturing into the Kuiper belt, humanity could achieve a deeper understanding of the forces that govern the outer solar system and the processes that drive its ongoing evolution. The remote icy body serves as a critical focal point for the study of planetary systems in their infancy. As one of the larger members of the Kuiper belt, it represents a class of objects that have remained largely unchanged since the solar system's formation approximately 4.6 billion years ago. These distant worlds, often referred to as fossils of the early solar nebula, offer a glimpse into the conditions that existed before the major planets coalesced from the primordial disk of gas and dust. The frozen celestial sphere's surface is a testament to the extreme environment in which it resides. Temperatures hover near absolute zero, at around -243 degrees Celsius. At such frigid levels, volatile compounds like nitrogen and methane freeze solid, forming a crust of ices that preserves the chemical history of the early solar system. This pristine environment is not only scientifically valuable but also serves as a natural laboratory for studying the behavior of materials under conditions far removed from those on Earth. One of the most intriguing aspects of this outer solar system world is its potential internal structure. While direct observations are impossible without a dedicated spacecraft mission, models based on its size, density, and surface composition suggest a differentiated interior. Beneath the icy crust, the trans-Neptunian body may harbor a layer of water ice mixed with rocky material. At greater depths, under the pressure of overlying layers, this water ice could transition to an exotic form known as high-pressure ice. Such internal layering is consistent with what has been inferred for similar-sized dwarf planets like Pluto and Eris. The density of the frozen celestial object, estimated from the orbital motion of its moon 2 Malawian quachas, indicates that it is likely composed of a mixture of rock and ice, with rock constituting a significant portion of its mass. This combination aligns with the idea that objects in the Kuiper belt formed in a region where water and other volatile compounds were abundant, but temperatures were too low for significant accretion of gaseous materials. These conditions contrast sharply with those of the inner solar system, where rocky planets formed in a hotter, more volatile depleted environment. The Kuiper Belt residence moon, 2 Malawian Kwacha's, continues to be a topic of intense scientific interest. With its dark surface and small size, this satellite poses unique challenges for observation, even with the most advanced telescopes. Nevertheless, the discovery of this moon has provided an invaluable tool for determining the mass and gravitational field of the parent body. By analyzing the orbital dynamics of 2 Malawian Kwacha's, researchers can refine their models of the dwarf planet's internal structure and gain insights into the processes that led to the formation of this binary system. The relationship between this icy world and its satellite raises questions about the broader processes that govern the formation of moons in the Kuiper Belt. In the case of the distant sphere, the leading theory is that 2 Malawian Kwacha's was created through a giant impact, in which a collision with another Kuiper Belt object ejected material into orbit. Over time, this debris coalesced into the moon we observe today. Such impact events were likely common in the early solar system, as countless small bodies collided and merged to form the larger objects we see today. In addition to its role in understanding the solar system's past, the study of this remote world holds implications for the search for life beyond Earth. While the frozen orb itself is unlikely to support life due to its extreme cold and lack of liquid water on the surface, it represents a class of objects that may exist in other planetary systems. The presence of water ice and organic compounds on its surface suggests that similar materials could be common in exoplanetary systems, where they might serve as the building blocks for life. Moreover, the exploration of this frozen celestial body and its neighbors could help scientists understand the distribution of water and organics throughout the solar system. These materials are thought to have been delivered to the inner planets, including Earth, by comets and other icy bodies during the late heavy bombardment period. By studying the chemical composition of Kuiper Belt objects, researchers can trace the pathways by which life-essential elements were transported across vast distances. Future missions to this distant celestial sphere are likely to revolutionize our understanding of the Kuiper Belt. A spacecraft equipped with high-resolution cameras, spectrometers, and radar instruments could map the surface in unprecedented detail, revealing the distribution of ices, organics, and other materials. Such a mission could also investigate the moon 2 Malawian Kwacha's, providing a more complete picture of the system as a whole. The data collected would not only deepen our knowledge of this specific object but also shed light on the broader processes that govern the formation and evolution of the outer solar system. The technical challenges of reaching the frozen sphere are significant, but not insurmountable. The vast distance, combined with the need for advanced propulsion systems and power sources capable of operating in the frigid, low-light conditions of the Kuiper Belt, requires innovative engineering solutions. NASA's New Horizons mission to Pluto and the Kuiper Belt has demonstrated the feasibility of exploring these distant regions, paving the way for more ambitious missions in the future. This icy body and its companions in the Kuiper Belt are more than just distant curiosities, they are windows into the origins of our solar system and the processes that continue to shape it. By studying this frozen world and its environment, scientists can address some of